Welcome everyone to our course Solar Photovoltaics. Today we have module 4 and lecture 2. In the last few classes we have started introducing you the concept of different generations of the solar cell. So far we have learnt about first generation solar cell, second generation solar cells, and in the last class we started with one particular kind of third generation solar cell, namely dye sensitized solar cell. And we have also learned that this idea behind the dye sensitized solar cell was inspired by the artificial photosynthesis. People thought that whether we can mimic the natural photosynthesis process in the lab, and what we found that the method of fabrication of dye sensitized solar cell was quite inexpensive, and also the processing method and processing cost is very significantly lower in comparison to the first generation and the second generation solar cell. In today's lecture we will learn about how to fabricate this kind of solar cell, and we will see that at the end of this lecture it is very easy, and even using some of the very day to day objects we can make this kind of solar cell. Okay, let us have a look on how to make dye sensitized solar cell. Today we are going to show you how to fabricate a dye sensitized solar cell. In next 10 to 15 minutes we will go through this process, starting from some simple components or elements. We will show you how we can make a DSSC device. Today along with me we have two students. In my left side Mr. Naveen Kumar Taylor, and on my right side Ms. Yukta. So, as you can see on this table, there are certain components are there which is used to make a dye sensitized solar cell. The first component, if you remember, we talked to you about two electrode. One of this electrode is a photoanode which is made on putting the ITO or FTO on a glass substrate. The second component is the semiconductor, which is titanium dioxide. So, as a semiconductor we are using this titanium dioxide here, which is kept in this bottle in a slurry form. The third part was a dye or sensitizer. You can use, as we mentioned, that any kind of dye or sensitizers, like for example here you can use a porphyrin dye, which is one of the components or constituents of the chlorophyll also, or you can use for example laser dye like rhodamine 6G. And then finally, to regenerate the whole process we need a electrolyte solution, and we are using iodine triiodide as an electrolyte solution. To complete this circuit we have to put a counter electrode. You can put or you can fabricate the counter electrode by making the platinum on the glass substrate, but in a very simplistic case I can even take a glass substrate and I can put this graphite layer on that, which will also be a conductive layer, and it can be used as a counter electrode. And finally, all the device will be sandwiched by using this clip. And to measure the current and voltage we are using here an ammeter, where you can measure it the current and the voltage. Okay. So, let us start this process one by one. So, first we will show you. So, this is a normal glass substrate. So, what is the difference between this glass substrate and this ITO substrate? So, as we said that this substrate is not conductive. So, how can we say that? We have this multimeter. So, for example if we connect the two leads of the multimeter here, you can see that there is no current inside the multimeter. But whereas if I take this another substrate like ITO, for example this one, and if I contact the two probes of the multimeter, you can see a current here on the multimeters. So, that is why we can distinguish whether a substrate is conductive or not. Now, what makes this substrate different from this substrate? So, one is we have in one of this layer is more shiny in comparison to the other. So, in one of the layer we put it in a very thin layer of indium doped tin oxide or fluorine doped tin oxide. In our particular case here we are using an ITO substrate. So, this is my photoanode. The next thing, to make the devices we need a titanium dioxide. So, titanium dioxide is a slurry, or titanium dioxide is a semiconducting material. So, we have to make a slurry of the titanium dioxide. So, slurry means some viscous solution. Titanium dioxide comes as a powder. So, we have to put that powder in some kind of solvent and control the viscosity to make the solution a viscous or semi viscous liquid, so that we can put and make a very uniform thin films on the glass substrate. And here we have done it by putting the titanium dioxide on a pH3 acetic acid solutions. So, what we will do, we will take this pH3 acetic acid titanium dioxide slurry and we will put it on a ITO substrate. So, let us do that. Okay. So, this is our ITO substrate. So, now let us take a slurry. This is So, this is our titanium dioxide slurry and this is viscous. So, we have to take it from this thing and then we will put it on the ITO substrate like this. It is really viscous. So, we are doing it 2-3 times to take it more of this TiO2 or titanium dioxide here. We need a thick layer because this thick layer will help you to absorb the more and more light, and as I said that this layer should be mesoporous layer, that means there can be lot of spongy structure inside it. So, then next thing is that, so you can see that we have put some titanium dioxide slurry on top of this ITO substrate. So, now I need to make a film from this slurry. So, how can I do that? So, I can do it either by spin coating technique or by doctoral beading technique, but since here the viscosity is very high. So, if I wanted to spin coat it, that means if I pour some solution which moves it by the centrifugal force and make a uniform thin film, that is not possible here, but we can do doctoral beading technique. It is very easy. You take another glass substrate like this and you hold this ITO substrate and you pour this thing, you fix it on the top of this ITO substrate and slowly roll it like this. You can even use the other substrate like this. You can say that we can make a so we have been able to make a film of the TiO2 on top of this conductive ITO substrate. Now, next thing what we need to do is that we need to make this structure mesoporous, that means we need to create a spongy kind of geometry in this substrate. How can we do that? So, TiO2 is a semiconductor. If we heat it beyond a particular temperature, for example 450 degrees Celsius, so this structure will become a spongy structure or a mesoporous structure. So, we can do it by putting on a heat substrate, so which we call is a hot plate, which is showing here. This is an example of a hot plate where you can control the temperature. In the hot plate usually we go to 100 to 150 degrees Celsius. For going to further temperature like 450 or 500 degree, we really need a specially designed chamber like furnace or vacuum furnace, but here we are just showing it as a low temperature sintering method. So, what we will do, we will put this thing on top of this substrate and we will keep the temperature on and we will allow it, as you can see from this dial here, you can control the temperature as well as you can control the RPM, that is the speed of the rotation. Now, if I put it on the this glass substrate on this hot plate, so you can see that the color will started changing. Now, let us wait for 2 to 3 minutes to observe a change of color or unless until these films become solidified. Meanwhile, what we will do, we will prepare a dye solution. So, as I said that this is the dye molecule or the sensitizers molecule, which is a porphyrin compound dissolved in some organic solvent. Here for this particular case we are using an organic solvent which has a name called NMP. Now, NMP is a highly polar solvent and this dissolves this dye molecule very well. You can, as I said that you can even use any solvent, you can use any fruit extract, you can use any laser dyes also as a sensitizer or dye molecule. Now, next thing what we will do, we will take this beaker and we will pour it on this solution, so that we can dip this glass substrate on inside these solutions after some time. So, you can see here this dark green color solutions, as you say that the DSSC color can be tuned and this green color is coming due to its absorption property. So, it is actually characteristics of a material. Now, we have our sensitizers molecule ready and now we are waiting for our titanium dioxides to become like more thick and more solid and heat. So, maybe we can increase the temperature little bit high, so that this process become little bit faster. So, right now can we make it something like like you can see that as I rotate this knob the temperature is changing. So, we fix the temperature here to 120 degree Celsius. If you look here the reading of the temperature is 120. So, it will take some time 2 to 3 minutes for this substrate to become the temperature of 120, and already if I touch it, do not touch it, although during the experiment you can feel the heat. So, this place or this substrate has really started becoming hot. And now on the other hand I have this electrolyte solution which is also ready, and this electrolyte solution is made from the iodine triiodide electrolytes, and we try to also add some kind of additive solvents there. For example, a common additive which we used here is 4-tertiary butyl pyridine. So, this the role of the additive is to increase the conductivity. We can add it finally at the end of the device fabrication, or we can even put a little bit amount of additive inside the electrolyte solutions. Now, we need to wait for 2-3 minutes, like so that this film becomes solidified, and as you can see that color has already started becoming change, and if you wait for 5 to 6 minutes it will become a white color things. In this particular example we are taking this porphyrin molecule, but we can also take some other molecule, right. We can take any kind of organic dyes or any kind of polymeric molecule, or even some inorganic dyes or laser dyes, quantum dot as a sensitizers or as a dye molecule. And even as a semiconductor, in this particular case we are using titanium dioxide, but we can even use zinc oxide or some other large band gap semiconducting oxide, provided they will be able to transport the charge whatever have been injected to this semiconducting oxide. So, as you can see that this film has already started changing its color, and it is becoming a from dark yellowish to like some grayish whitish, right. We need to wait for another 3-4 minutes so that it really changes color and becomes a solid film, so that we can take out this film from the here and we can dip it inside our dye solution. So, usually what we do, like we take this titanium dioxide coated glass substrate and we put it in a muffle furnace which is a specially designed furnace, and we heat the substrate at 450 degrees Celsius, and we kept it to 3 to 4 hours. Within 3 to 4 hours, so the titanium dioxide not only changes crystal phase, it also made it like more mesoporous structures. But here we are doing a low temperature sintering for demonstration purpose. So, here we are trying to heat it at 120 degrees Celsius, and we wait how much color change we can see from here. Okay. Okay, the solvent whatever is inside this titanium dioxide slurry, that is slowly evaporating, and the film has been started drying. Although it has not dried completely, there are still some liquid portion, we can see it here, and since it is a very viscous, like the color is yellowish. I think we can probably take it out. We can take it out using a tweezer and then dip it inside this dye solution like this. So, usually we dip it overnight, but here we will try to dip it for 1 minute, and you can see that the color has been started changing, and it will depend upon the absorption coefficient of this the dye molecule. So, we just soaked it here and we make sure that the substrate get as much as dye contact area as possible. That is why I tilted this beaker little bit, as you can see here. another trick which we do that, like usually we dip it inside the dye solutions as soon as we take it out from our hot chamber. Now you see that the titanium dioxide anode has started absorbing the dye molecule, the here sensitizes porphyrin. Meanwhile, it dips it, we prepare the counter electrode. So, let us say this is the glass substrate, now which is one part which is left as a glass substrate. Now, this is the pencil which you use for writing every day, but you can even be useful for making a counter electrode. How we can make it? Like we can put it on the top and put it like that. So, this graphite piece we can take it. Okay. So, we see some color changes, and because the substrate is very shiny, like and reflective, probably we do not see the color change, but if we do the same thing on a glass substrate, you can see it like here. Yeah, like here you can see this. So, you can see that there is a layer of this carbon graphite has put on this glass substrate, and this has become conductive. So, to match the size or dimensionality, let us take this as a counter electrode. Okay. And I have a binder clip like this one and this one, which is used to sandwich these devices, and finally, we can take it out this devices, and if we empty it, let us say we empty all this glass side or ITO side from here and we put it back, and then we take it out. You see there is a color change, you can clearly see there is a color change. So, now this TiO2 layer has started absorbing the porphyrin molecule. Now, whatever the loosely bound dye, that we can wash out with some kind of solvent, or here we are just trying to wipe it out. And I put it back on the substrate. Okay. So, the photoanode is ready now, and my counter electrode is also ready. So, next thing is to make the complete sandwich type of structure. So, what we will do, we will take this photoanode and we have this counter electrode. So, we will sandwich like this, and then we will put this 2 electrode. First I will put 1 electrode, so that the contact between the counter electrode and the semiconductor is fine now. Now, what happens if the light falls on this TiO2 layer? So, TiO2 layer has absorbed the dye molecule. So, the dye will absorb the electron and it will go from its valence band to the conduction band, and then it will inject that electron to the titanium dioxide, and that electron now will percolate through the external circuit. To regenerate this process, we mentioned that we need to add some electrolyte. Now, usually the electrolyte is done by putting a drill on top of this glass side, but here we can also put the electrolyte by the diffusion process. So, we need to have a pipette like this, and we will take few drops of the electrolyte like this, and we will add it slowly like drop wise like this. So, the electrolyte solutions is now diffusing inside the TiO2 layer, and we complete the device configuration by putting the counter electrode on the other side. Okay. So, my device is ready. So, which is sandwiched between a cathode and anode, and the titanium dioxide is containing a particular dye. In this particular case, it is a porphyrin dye, and we put few drops of the electrolytes. So, the dye sensitized solar cell or the grad gel cell is now ready. The next thing is that to characterize the solar cell. Now, there is a very standard instrument to characterize the solar cell called solar simulator, where we can simulate the artificial sunlight, like we can take a broadband light source and pass through a filter which is a AM 1.5 filter. We have already introduced you the concept of AM 1.5, so that it can mimic the sunlight, natural sunlight, and then the light falls on the material, it absorbs the light and it converts the electron into the charge into the electron hole pair. The photons is converted to the electron hole pair, and that passes through the external circuit and we can measure that thing. But here in our daily life or in the lab, undergraduate lab, we can also use a multimeter like this. So, all we have to do, you have to have this device, and then if you wanted to measure the current, so you can flip it like this. Okay. So, one of the substrate is transparent, so light falls on it. So, I will put one contact on the conducting substrate and one contact on the back substrate like this, and you can see like right here it is in a, we can also change the, we can, if you, this is using this multimeter, we can also measure the current and voltage from these devices. If we know the current and voltage for different values, from a calibration curve we can find out what is the fill factor. If we know the fill factor, if we know the current and voltage, and if I know the input power, then we can calculate the efficiency of these devices. Okay, so now our DSSC device is complete. Now we can put 2-3 of these devices to make a module, and we can use it for practical application. Thank you very much.